Hello everyone, my name is Taudam Vilip Singh from NIT Manipur, and my topic is on force extension behavior in energy polydisperse polymers. The response to an external force given to a single chain polymer has not only been studied theoretically using Monte Carlo method, bone fluctuation method, Langevin dynamic simulation, but also experimentally in investigating biomacromolecules such as DNA, RNA, polysaccharides, and proteins. And they are done so with the use of maybe single molecule atomic force microscopy. It can be done using optical and magnetic tweezers as well. The force extension behavior of a single chain polymer can be studied with the application of these tweezers. The study of such response is of importance as they are usually linked with the function as well as conformational changes in biomacromolecules, the set biomacromolecules. For instance, when a single DNA is tweezed, it could give light to the conformational changes in the chain when subjected to forces in a biological regime. The different biomolecules found in nature have different force signature when they are subjected to loading. So every one of these biomacromolecules have force signatures. These are my motivation. So we consider ourselves a polydisperse polymer. The energy polydisperse polychain is studied in an implicit solvent system under the influence of a solvent which has been replaced by an effective pairwise interaction between the monomers. This is advantageous in considering the large computational time when the interest of the study is toward time scale rather than the solvent dynamics. The polymer system under investigation, this is not meant to imitate one which is chemically specific, but it rather aims to eliminate the generic behavior of the force extensionate heteropolymers, which are different in chain length as well as interaction energies between the monomers. The type of simulation is a coarse grain one, and it is also a molecular dynamics. The monomers have interaction energies epsilon 1, 2, 3 up to n, and these are derived from two types of distribution. One of them is a normal distribution and the other is the uniform distribution. And we define what is called a polydispersity index, delta, and it is given by the standard deviation by the mean energy. And this mean energy is fixed for our study, and it is 2.5. Here we have a polydisperse energy chain of chain length 512. So the different colors indicate different energies that they possess. So after performing this molecular dynamic simulation of this energy polydisperse polymers, the results are compared to that of homopolymer 1, where the interaction energies remain the same, which is fixed at 2.5. So our system is a coarse grain 1, and it is done under molecular dynamics. It is simulated so in LAMS package, large scale atomic molecular parallel simulator. In that we use two types of potential. The one is the Lennard-Jones potential, also known as 12-6 potential, and another one is the Finney potential for making the bone seem like a spring. So these are very common type of simulation. So while performing molecular dynamic simulation for studying force extension behavior, we use single energy polydisperse chain at a time in a collapsed state in an implicit solvent to study the force extension response. The considered globule, we considered a globule which is short of sphere. What happens is that it is considered at temperature 1. The normal as well as uniform polydisperse polymers are taken at 3 polydisperse indices at delta equal to 4, 9 and 13%. For every delta, not fewer than 10 different configurations at a collapse state are considered. So the length remain the same. The potential use are Lennard-Jones and Finney potential, and we use this simulation on NVT ensemble at a periodic boundary condition, and the molecular dynamics steps is for our production run is 6 times 10 to the power 7, and the time step for our simulation is 0.05. So these are in Lennard-Jones units, so they are unitless. So here we have our illustration. So the first one, this one is considered at temperature 1. From temperature 1, what we do is that one end of the polymer chain is fixed and a force is applied to the other end. The one end is fixed, on the other end force is applied, and this is but an illustration. One is for the normal at 4%. We considered at 4%, 9% and 13%. This one is for 4% for normal distribution, and the energy range is from 2.4 to 2.5. So what we did is that when force is applied, when the force is 40, we can see that it starts to stretch, but with application of greater force it stretches. At about 70 it is stretched to its full length. So these graphs show how polymers extend under the application of external constant force. By constant force I mean this force is constant. What is increasing is the time, in Lennard-Jones time. So some of them get stuck in a metastable state, and which is also what happens in a real system when polymer gets stuck to a metastable state. So the result is here. The result is that we check the force extension behavior of energy polydisperse polymer by plotting the average end-to-end length reduced by its maximum length L as a function of force. So we check how the end-to-end distance changes as a function of F. Its force extension curve represent the average of 10 or more realizations simulated in the same condition, except that they have different collapse state as the initial condition, and we call them replicas. So these are the result that we find, and then in short, what we find is that up to about this 30, no significant difference in end-to-end is observed, but beyond this 30 they start to spread. So they start to spread, and between 50 and 65, from 50 and 65, somewhere around, we can find the transition from a globule state like this to a coil state. This is what we found. And the thing is, the homopolymer required comparatively greatest force as transition into extended coil at F equal to 67. So this is our finding for the two types of distribution. Thank you for your kind attention.